Buenas tardes, profe.
Buenas tardes. ¿Cómo están todos? ¿Alguna prediscusión antes de que lleguen los demás?
Hola, profe, buenas tardes.
Buenas tardes.
Sí, profe, justamente quería preguntarle, he escuchado que me parece que se está discutiendo ahorita mm, una, una decisión para aplazar el semestre tal vez, o para parar el semestre una semana o 2 semanas, me parece que es. No sé si usted tiene conocimiento de eso.
No he escuchado de eso específicamente, no. Hasta ahora tenemos dos reuniones del Consejo Académico planteadas, pero ese tema no está ahí, no está en esas agendas. Pero voy a averiguar.
Sí, profe, porque
Tú
se ha
dices,
hablado
tú
bastante.
dices la idea es detener el semestre completamente en las clases que estamos dando y todo, ¿o cuál es la idea?
Sí, o sea, eso es lo que escuché, que la idea era detener el semestre al menos por una semana
Ajá.
para poder solucionar los problemas de chicos que, por ejemplo, no tienen internet en su casa o en general, porque debido a que, por ejemplo, esta crisis sanitaria se dio el día jueves, que nos mandaron un correo diciéndonos que nos tenemos que ir a la casa y el día lunes ya empezamos con las clases online.
Ujú.
Entonces, como que no hubo un tiempo para que los chicos se puedan organizar, para
Ya.
que en general nos podamos organizar y tal vez buscar los lugares adecuados para tener las clases online.
Ujú.
Entonces, hay algunas, bueno, puedo hablar personalmente que se nos ha ido acumulando la materia poco a poco, entonces como que hay muchas cosas que todavía tenemos que igualarnos. Y incluso los chicos que no tienen internet, me imagino, deben estar mucho peor con este tema. Entonces, es una propuesta que no nace, bueno, de estudiantes de IH, me parece, sino más bien es algo que se está discutiendo a nivel nacional
Ujú.
en varias universidades del país. Entonces, eso, bueno, quería preguntarle si tal vez usted sabía algo.
No, 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 la verdad es que no me han consultado ni han anunciado eso por un medio que ya haya visto. No sé si tuve un par de reuniones antes de la clase, así que no sé si durante eso me enviaron un correo que no he leído. Pero no, pues yo estoy pendiente de eso y voy a chequear con Graciela a ver este, qué es lo que está sobre la mesa.
Ya, profe, muchas gracias. Y bueno, desde mi opinión muy personal, que sí tomen en cuenta eso, porque como le comento, o sea, tal vez, bueno, nosotros tal vez no estamos bajo esa realidad, pero incluso hay chicos que tal vez, no sé, sus padres incluso viven del trabajo del día a día, entonces
Claro,
ahorita creo que están más preocupados por otra situación que por estudiar, ¿no? Creo que
claro.
hay
Mm.
prioridades, entonces
Sí,
no me parece una idea.
a mí me ha contactado un estudiante, no, creo que es de semiconductores, que me ha dicho ese problema, que ha tenido problemas con el acceso a internet y ese tipo de cosas. Pero lo que, digamos, yo pensé que ese tipo de cosas, yo por ejemplo estoy tratando de dar las clases, eh, me solapo un cuarto de clase anterior, entonces vamos a un ritmo relativamente más bajo, tenemos todas las clases grabadas de manera que se pueden consultar. Por ejemplo, estamos abiertos a retrasar un poco las tareas en función de esas dificultades también y así yo creo que también es otra manera de sobrellevar, ¿no?
Ujú.
Pero se verá cuál es la mejor, cuál es la más idónea, ¿no? Para afrontar el problema, pues, ¿no?
Sí, profesor. Para que lo tengan en cuenta también si es que
Ok,
se llega a tomar una decisión importante.
ok,
Y eso más que nada, porque, como le digo, sí existen muchas realidades que tal vez ni siquiera conocemos, muchos
claro.
problemas a los
Sí.
cuales los chicos están expuestos. Y todo esto se debe incluso por el hecho de que la universidad, bueno, la empresa pública nos mandó un correo diciendo que tenemos que desalojar las viviendas. Entonces, por ejemplo, si tal vez hubiera habido una mejor organización, nos hubieran comentado que se van a empezar a recibir clases online, tal vez muchos chicos que no tienen internet en sus casas se
Claro,
hubieran
se hubieran
podido quedar.
quedado, claro. Sí, sí, eso fue
Entonces,
medio confuso, eso lo admití. Yo no sabía tampoco, yo estaba confundido un poco de qué es lo que estaban pidiendo. Pensé al principio que era opcional, después obligaron. Unos estudiantes dijeron que no y se quedaron. Entonces fue un poco desorganizado ese proceso, ¿no?
sí, profe, y de lo que a mí me comentaron es que, por ejemplo, hay un señor, hay un padre de familia que averiguó con la persona responsable de esto en Siempre P, y esta persona de Siempre P le comentó que esta decisión vino desde la universidad.
Ujú,
Entonces, mm, no sé qué pasó ahí. No
claro.
quisiera creer que es debido al hecho de que, por ejemplo, ese día justamente nosotros teníamos una asamblea general entre profesores y estudiantes, y
Mm,
justamente ese día íbamos a hablar sobre el tema de los concursos de méritos y oposiciones de los profesores,
mm,
tal vez tomar decisiones como estudiantes y también los profesores desde su gremio, como usted mencionaba el otro día. Y justo ese día es que nos mandan este correo diciendo que tenemos que
mm.
desalojar las viviendas y luego en medios de comunicación dicen que no, que en realidad era opcional, si el estudiante quería se podía ir, si no se podía quedar. Y luego tenemos las clases online desde el día
Y tengo
lunes.
entendido también que no pueden regresar, que nadie puede regresar tampoco, ¿no?
Nadie
Que
puede
eso,
regresar.
exacto, que hubo este par de estudiantes que están ahora en Ibarra, creo que es porque no pudieron dejarlos entrar en Yachay, ¿no? Pero bueno,
Efectivamente.
sí.
Entonces, hay un tema, varios temas que no están muy claros y
Mm,
la universidad debería hacerse responsable, creo yo.
claro. Muy
Profe, y
bien.
al final, muy buenas, ¿cómo están? Profe, y al final, ¿en qué quedaron respecto a la universidad y respecto a los nombramientos con los profesores?
No, no, es
De,
que eso, el proceso tenía, tú dices el proceso del proceso de revisión de los concursos. Nosotros, los profesores que estaban involucrados, tenían unos plazos para entregar unos documentos y entonces ese plazo se venció ya hace 2 semanas, el martes, pero antes de eso hubo una asesoría que hicieron los profesores y en vista de toda la emergencia era inaceptable que para empezar teníamos que entregar los documentos en físico, en talento humano, donde no iba a haber ningún personal presente, ¿no? Entonces, todo ese conteo de días se suspendió hasta que se levantara la emergencia. Entonces, eso no ha avanzado más desde aquel momento. ¿Cuántos habemos ya? 1, 2, 3, 4, 5, 6, 7. Ahora la expectativa somos 9, ¿no? Somos 9 en el curso de Sólidos 2. Vamos a empezar clases entonces. Okay, so let me share with you my sketchbook here. Okay, so last time, is the audio fine? Everybody listens to me correctly?
Yes, teacher.
Yes? Oh, perfect. Okay, so we were starting on the interacting Fermi system. Okay, so in order to go beyond what we've had been doing before, is that before we had a single particle operator, right? So a single particle operator is an operator that depends on a single spatial coordinate, okay? only one coordinate. Okay, this is in direct space. If you were talking about Fourier space, there will be just one k associated with this. Okay, so for the interaction. So this is a one body interaction. Okay. Now we're going to, and this for example addresses external fields. External fields. Okay. Now we're going to go with the two-body interaction. Okay. Which is a little more familiar to what we call interaction. Which is now we have, for example, a Coulomb potential. Okay. Exempli gracia. Okay. So you learn to do this. You've seen this acronym here. This comes from Latin. Exempli gracia. Okay, so the Coulomb potential. This is, for example, the Coulomb potential. Okay, and the Coulomb potential is now an operator. Okay, that in principle depends on two coordinates. Okay, in the case of the Coulomb interaction, okay, because of a translational invariance, and we'll go into that topic in a little while, though I explained it in class when we were still not under the emergency. So we have this is depending on r minus r prime. Okay, so this only depends on the relative positions of these two particles. Okay, while here this is a much more generic potential where you can depend either in the specific position of r1 of r and the specific position of r prime. Okay, so here in the case of the Coulomb interaction, it's a central potential, okay, which you have seen in the case of gravity also, electromagnetism, okay, and there are other interactions that have this character also, okay, for example, the weak interaction, the strong interaction also have this character, okay, so it depends only on the relative positions of the two particles. So this implies translational invariance. Translational invariance. Okay, and we'll exploit this shortly. Okay, so we have that my two-body interaction is not only two-body, that is, it has two labels, but the dependence on the two labels is in a very specific way, in this way, and this is the character of many interactions in physics. Okay, so we will have a total Hamiltonian, which has now a kinetic part, which is going to be H0, and then we'll have this two-body interaction that I'm mentioning here. Okay, and this is going to be just the kinetic energy. Okay, so this is and we're going to ignore for now, for easiness, although we know how to handle that, ignore external fields. Okay, so we could put something additional here, plus a u that depends on a single coordinate, that would be an external field. Okay, but we don't care about this extra term, so that we just addressing two-body interactions here alone. Okay, any questions? Is it clear?
Is equivalent to have two potentials in terms of two coordinates r and r prime and the r minus r prime?
Is it equivalent?
Could you explain in more detail the part of the central potential?
Oh, because it's just that, I mean, this would be a much more general potential. Okay, remember, let me try to draw. So So when I'm talking about this guy, okay, I say that the interaction may depend on the specific R and the specific R prime that I have, okay? So, for example, two particles that have the same value of R minus R prime, okay, would interact differently if the two positions were here, okay? So imagine that if I had this two, if I have this potential, this would be different from this. Okay? So this is what I mean that it's not translational invariant. If I translate this separation, okay, this separation here, to this particular point, then this potential can change, okay? But this potential does not change. You see my point? So this depends on two coordinates, but these two interactions are the same for this potential, but not for this one, okay? Because this depends separately on R and R prime. This only depends on their difference, okay? So
of the distance between the two
right,
parts.
so if this distance is the same as this distance, then this potential is the same.
The interaction is the same.
Right, exactly the same. This value, this is going to be a certain C number, okay, a real number, okay, this is going to be a real number. This real number is the same for this pair and for this pair. But if you describe something, this is more general, this might vary in space, for example, okay? So now your potential depends on where these particles are specifically, besides their separation, okay? So this is a more general one, more general, okay? Not translational invariant, okay? So this doesn't incorporate translational invariance. So for example, in a potential that depends like this, you would not have momentum conserved. So this is a very important point we're going to make. But for this potential, you would have a momentum conserved because it doesn't depend on the specific positions of the particle. You can translate the two particles together anywhere as long as you keep the relative distance and the potential is invariant. Okay, so that's a point. Is it clear?
Thank you.
Okay. Okay, so okay, so as we choose the eigenvalues, eigenfunctions of H0, okay, this is the Hamiltonian we can solve, okay, as our basis, then, okay, this implies that our bases are going to be plane waves, just the kinetic energy operator, which will be this form here. Okay? And we know that the eigenvalues associated with this basis is going to be something that is has k as a good quantum number. Okay. Okay. K is a good quantum number. This is a language you will hear a lot if you're in quantum mechanics. Okay. This is just that we can label the states in a unique way just by giving you the value of k. The rest are related to the Planck's constant and the mass, the bare mass of the electron, okay? This is the case if only we had the H0 as the Hamiltonian, okay? And then we add, okay, we add V operator, R minus R prime, okay, as a perturbation. Okay? Okay, so Okay, so how do we advance with this from the point of view of diagrammatics? Okay, again, for the one-body interaction, we had our interaction drawing was related to this blob. Okay, so we had 4 types of blobs. Okay. Okay, these blobs. And these blobs had, as we had a one-body interaction, we should just have 2 handles on them. So a handle that was going in and a handle that was going out. Okay, those are not propagators, they're just telling you how I can insert propagators into the problem. So we could have a K1, okay, that went to a K2, or we could have the other way around. We could have a K1, which went to a K2, okay? And then we could have particle hole handles where you have something going in, K1, and we had, and let me put sort of an intermediate momentum here, because we're always ending up with a particle above the Fermi sea. So we have a handle like this, or we had a handle like this. Okay, so these are the blobs for the one body. Okay, one body operator. We have these blobs. Okay, and remember we did all our diagrammatics before using just this single blobs with 2 handles, and this is the one body interaction. Okay, one body interaction. Okay, 2 handles. Okay, any questions here? So now we're going to the 2-body operator, the 2-body interaction. Okay, so in the 2-body interaction, now we're going to have 2 particle labels coming in. Okay, so we have something like this. So one particle getting scattered and the other particle, so this is 2-particle potential. Also, we have a second particle coming in. Okay, so for example, the first particle can have a label M. This is momentum. Okay, N, K, L. Okay, and we can represent, and we will use here the wavy line here, but in the literature you'll find things like this, depending on the field. For example, in phase transitions, you'll find it like this, or you might find something like this, okay? And you might think this intermediate line here as the particle mediating the force. Particle mediating. Okay, interaction. Okay, so for example, in the Coulomb field, we know that the Coulomb field, the electromagnetic field, is made of photons. So one electron comes here with momentum n, the other electron comes here. Okay, so we can put E interactions. Okay, through the Coulomb. Okay, so the Coulomb potential is the potential through which 2 electrons can scatter off each other. Okay, so one electron is coming with momentum n, the other m, the other one with momentum n, and then they exchange a photon, for example, and they scatter. They change their momentum, each of them. Okay, so this is going to be the Feynman rule associated with this is going to be assigned minus I over 2, and then we're going to have a matrix element that has 4 labels. Okay, and the order of these labels are so that these are the incoming electrons, and these are the outgoing electrons. Okay? And as we wrote also in the one particle picture, K, L, M, N is going to be this integral. Okay, remember we're doing things in second quantized form, so we need these prefactors as we know now how to construct one and two body interactions in second quantization. So this will be the prefactor that you use in your second quantized form of the operator. Okay, we have K, R, K, L, R prime. Okay, notice that these two labels are the out labels here. Okay, then you have the potential in real space. Okay, and then you have the other two labels, M. Okay, so this will be the matrix element you have to calculate. So you put in your basis functions. Remember, these are the basis functions here, and you chose them so that you know them and you can calculate. You know the interaction. You can put the basis functions here, and it's a matter of doing this integral to determine this intensity here. Okay, so that would be, you know, the full way to calculate the second quantized form of this two-body interaction. Okay. Any questions here? So one thing I wanted to point out, so these two, for example, N and L, so you see N, you see the structure of the diagram, N and L have the same R prime. So these are described, so you sort of I understand that this will be the R prime part of the diagram, and this is going to be the R part of the diagram. Okay, so this one electron has described by this coordinate, the other electron is described by the other coordinate. This is very intuitive. So this is this branch of the diagram, and this will we will understand now the graphs that we're going to use for the different processes that can happen. Okay, so this will be assigned the R prime label, and this will be assigned the R label here. Notice a symmetry that we have of this matrix element, a symmetry of this matrix element. If you can notice there is a symmetry exchanging R with R prime. Okay? That means that if I change all R's for R primes and R primes for R's, okay? Here, nothing changes, okay? Here, I would just have a swap of these two, okay? Here, I will swap of these two, but then I can exchange these two differentials also, so the integral will not change, okay? Integral value does not change. Okay, so later we will refer to the structure of the integral to see what matrix elements are equivalent to one another. Okay, so from this also, this also will imply, and I leave it to you to understand. If you don't understand in like 10 minutes, ask me again, okay? But then I can also swap. I can also write it like this. Okay? So notice that if I change K and L and simultaneously M and N, okay? So these two are the same matrix elements. And you can see just by swapping the labels inside the integral, you see you obtain exactly the same thing just because of this symmetry here, okay? So bear this in mind. I mean, the symmetries of V are the symmetries of this integral, okay? So we see under which exchanges in this integral we obtain exactly the same value. So these will be invariances or upon changing the labels this diagram. Okay, a big diagram here. Is this clear? Anyway, we'll use it soon. Okay. So what type of diagrams can we have so that this interaction, as this in the same sense as the blob before, will serve us to build particle hole processes. Particle hole processes. Okay. So what are these particle hole processes are going to be built from these basic units. So I can have, as before, I can have something like this, my interaction. Okay. Then we have this one going here and this one going here. Okay, so let's label them here. So we know M, N, K, and L. Okay, and this implies that the energies associated with them are above the Fermi C. Okay, the energy of K is also above the Fermi C. Okay, and the same for the other two. The energies of N and L are above the Fermi C. Okay. But I can have another process where I can have, for example, these two guys here, M and K, but then, okay, I can have, for example, one hole here turning into a particle here. So let's call these two N and L. Okay, so this implies that EM and EK are greater than the Fermi energy. Okay, while En is smaller than the Fermi energy. Okay, En is going back in time, and here we can include in the club El is also greater than the Fermi energy. Okay, and you can imagine all the other guys, okay, all the other guys that now will be two processes like this, okay, and finally we can have a process where both particles are propagating back in time, so we can have something like this. Okay, so M again, M, K, and L. Okay, now all of these guys are going back in time. And so all of them are represented. So these are only whole processes, okay? Okay, these are particle hole, and these are particle processes. Okay, and you can imagine some other, for example, another example of this would be something that is here. That would be a particle hole process. It would be like this. And I leave you to label this. So we go like this. Okay. And the other one like this. Okay. So this will be another process like this where we have particles. These are holes going back in time, particles going forward, and these are holes going backward and particles going forward. So in this case, we have two pairs, so EM and EN are less than the Fermi energy, okay, while E sub K and E sub L are greater than the Fermi energy. Okay. Okay, so we have everything set up. Any questions before proceeding? Okay.
How we can differentiate what is the difference between the Hall process and the particle process, Mr.?
So here in the diagram would be some process where, for example, the interaction, here we have an electron coming in, okay? So it interacts, okay, with a hole that's below the Fermi energy, and their scattering produces an electron above the Fermi energy and another electron in the state K. So this is just an electron coming in, the interaction, you turn on the interaction interacts with a hole that's made in that exists below the Fermi C, okay? We can have holes above the Fermi C, okay? So we have only holes below the Fermi C, and then this hole gets filled in, and you produce a particle in the L state and the K state. Okay, so this is just the types. We will see shortly what kind of interactions we're going to have. But the thing is that this interaction allows an electron, because the electron has positive negative charge, interact with a hole which has positive charge. So this is governed by the Coulomb interaction, and this interaction produces a production of a particle above the Fermi energy, okay, and two particles above the Fermi energy, okay. So this is, I mean, this is not a real process yet, because we need to specify what states I'm injecting, how they're going to interact, and then how they're going to come out from the system, okay. But just judging from the interaction, this is what is going on, okay. Electron hole interactions here, okay, producing two electrons, or two holes, okay, interacting and producing two electrons, okay, and so on, okay. So when we draw the specific diagrams, then we will see the process in a more concrete fashion, okay. So we concluded, okay, that the Coulomb interaction, okay, is translationally invariant. Okay, this means that momentum is a good quantum number. Okay, this means that momentum is a good quantum number. So that means, among other things, that momentum is conserved. Okay, so what does that mean? Momentum is conserved means that if we grab the labels, okay, we have the incoming m plus n. These are the incoming momentum, incoming. Okay, has the sum of the two momentum, okay, as we know from collisions in classical mechanics, right? It has to be equal to the outgoing momentum. Outgoing. As simple as this. Okay, so quantum mechanics is also a slave to momentum conservation. So we have that this must be satisfied in any process in which I involve this interaction. Just because the interaction is translationally invariant, this means that momentum has to be conserved. If it's not translationally invariant, then momentum is not conserved, okay? So this is implied by momentum conservation. Okay, a must. This is the way you say it in English. A must is something that must be obeyed, must be obeyed. And you know then, from very general principles, okay, so some friend of yours or your advisor is telling you, look, let's calculate these things with the Coulomb interaction. And the momentum is not conserved, something's going wrong. Okay, so this is what you can judge that the problem is wrong by inspection, right? You know that this is something that must be satisfied, and if it's not satisfying the calculation, you did something wrong in the calculation. Okay, so this is one of the guides that physicists have in order to just penetrate the problem without doing any calculations. So symmetries is something that should be conserved. If you start a Hamiltonian with an initial symmetry, and then you derive a result that breaks that symmetry, then something went wrong in the middle, the math is wrong, you know, you made some mistake in the calculations or something, because this must be preserved all through the calculation. It's something like dimensional analysis. You know, you can't end up with an energy in terms of dynes or an energy in terms of meters, because you know you did something wrong in the calculation. Okay. Okay, so let's see what the immediate implications of this are from the point of view of the diagram. So if I have a simple diagram like this, so two particles interacting above the Fermi sea. Okay, that's something like this, nicely drawn. So we have M, K, N, L, okay? Then by momentum conservation, in principle, you could draw something like this. So let's suppose we keep the labels M and N. They come in, M, okay? And now I'm going to draw a second line, but I'm going to expressly conserve momentum here, because if these labels, that means that these labels are not independent because they're connected by this rule here, okay? So this means that I could draw something like this. Okay, so here is a line coming in. So if I lose now a momentum here, that's so nice. Let's see if I put it like this. Okay, so I have the momentum Q is lost here. So now M goes in here. It loses the momentum Q, whatever particle is carrying that momentum. You assume that it has to be able to carry that momentum. Then this is going in. And then if we have N going in on this side, let me put the vector so we have a consistent diagram. This is coming in, and then this must be added, and this will be N plus Q. You see? So I just applied here. Now I apply a momentum labeled to the interaction. So the interaction takes away, for example, we know that photons have momentum, right? So the electron comes in, emits a photon, okay, through the Coulomb interaction, and it loses that momentum. So this will stay here, okay, so the M minus Q on this side, and then the particle coming in receives the impact from that photon, and it comes out with an N plus Q here, okay? So we might write this interaction like this. B, and then we have the order of this was what? Let me just make sure that I have the orders of the labels correct. KL, okay, so KL are going to be these two. So we have M minus Q, okay? Then we have N plus Q, and then we have M and N. Okay? So this is one way to see it, but the other way to see it is just that you label, and we will use this notation, okay? This is the same as writing just V of Q, okay? So in Fourier space, okay, in Fourier space, we might write it like this because it only depends on this intermediate momentum that it's being exchanged by the two particles. Okay, but for now we'll do it like this, and we'll worry about the specific labels we have. Okay, okay, use sometimes. Okay, is it clear? So we have that.
Yes, sir.
Yes, what's up? Any questions? Oh, is it clear? Okay, it's clear. Okay. Okay, so now let's draw here the most sophisticated. This is going to be the most sophisticated diagram we're going to treat in this section. Okay, most sophisticated diagram to see that. Okay, sophisticated diagram. From this diagram, we're going to give this diagram will inspire the sort of the last topic of this section, which is the screening of the Coulomb interaction. Okay. So the most sophisticated diagram is something that goes like this. You have a propagator coming in. Okay. So let's do this in KT space. Okay. In KT space, so a particle comes into the problem in the in an eigenstate of the h0 of the free Hamiltonian. It has momentum k. Okay, at time t, it interacts. So I draw my wavy line here. Okay. And after this interaction, it ends up having some momentum. It propagates for another distance here, and then it interacts again. Okay? And then it goes out. Okay, it interacts again at T prime, and then it goes out at T2. Okay, we know here that if we enter with momentum K by momentum conservation, whatever happens in the middle, if a single line survives, the single line has to have momentum K because we conserve momentum all through the process, okay? And here in the middle, we'll have this strange structure here. We'll have this bubble here, and we'll have arrows going in and out of these vertices here. So we'll call these here vertices. Okay. Okay, so let's try to label everything so that we have conservation of momentum. So if we say that now the interaction takes away a momentum q, okay, then k loses q and is left with the k minus q on this side. Okay, and now you're injecting q onto this two propagators here, this particle Hall propagator. So I'm going to label this, the top one, as L. Okay, so now we enter here, we enter with Q and go out with L. So we have to add something here so that when we add this piece to this piece, then we end up with L. So this should be what? L minus Q. Okay, if you inject into this node, into this vertex, okay, L minus Q, you add it with Q and you get L. Okay. Okay, it's like an electrical circuit. So this might be the current. The current is L minus Q. You add a current of Q, so you cancel this minus Q by adding this Q here, and you're only left with L. Okay, and we go around now with L. Okay. We go around now with L, and we are left, after reaching this vertex, we leave with the L minus Q, so we must have Q going down here. So now we have everything labeled, because now K minus Q, and you add a Q, you're left with K. So, okay, momentum conservation. Conservation. Okay, is this clear? Any questions as to how I label this? Anything you want to clarify? So specify the times, okay, the interaction times at t and t prime. Then you have all the labelings of the momentum, both for the interaction lines, okay, and the particle hole lines, which are these, okay, these bubbles here.
Maybe with the origin of the interaction at time t, that we have q that is going, is something that can cause that effect.
So, well, as I said before, for example, the mediator of the Coulomb interaction, okay, is a photon. So I can have an electron here. It emits a photon with a momentum, because the photons have momentum, right? So it emits a photon with momentum q, and so it's left with momentum k minus q, okay? And now this photon hits an electron with momentum L minus q, and it hits a photon with momentum q, so it's left with an electron of momentum L, okay? And then this electron of momentum L emits a photon again, and it's left, okay, with a hole of L minus q, okay? And then we hit the electron, okay? The photon hits an electron with k minus q, and it's left with we were left with an electron with momentum q, with momentum k, okay? So this is essentially the process that we're considering, okay? This is a little more complex. We're going to consider other more simple processes, but this is so that it would be challenging to do the momentum conservation bit, okay? Okay, so do you understand why I put L's and L's minus Q? With just, I postulate this Q. Obviously this Q we have to remember that this interaction can happen at any T and T prime. So this will be integrated over, okay, integrated. The same happens with the photons, okay? So the photons can be Q, but this is an internal variable, so this must be integrated over, okay? So T's, okay, the T's are integrated over, okay? And the Q and L are also internal variables are integrated over, okay? This is the same that happened when we had the one-body interaction, remember? And we had something like this, a one-body case. Okay, and we have something like this. So K1 was coming in, okay? And we have a blob, and then we have some intermediate momentum, so this is L, okay? And then this goes back to K1. Sorry, K2. So remember these two, K1 and K2 are fixed. These two are fixed by the Green's function we're trying to calculate, okay, fixed. But this one is free. So we integrate. Okay? So this is the one body case. And we do the same for this one, okay? We just put one body case and separate this. Okay? The same is for this one. Now we have intermediate Q's here, and we have to integrate over these intermediate Q's because these can change all kinds of momentum depending on what the interaction is, okay? We can emit all kinds of photons from this interaction depending on the nature of the interaction. Maybe the interaction just connect with one particular photon, in which case, okay, we'll have a delta function for that photon momentum. Otherwise, we have to sum over the free parameters, which are Q and L. Okay, so that's the idea. Does it answer your question?
Yes.
Okay, so we have this important restriction, which is the momentum conservation. Okay, let me put here a very important point, which is maybe something you've heard before. Nevertheless, energy is not conserved. In the intermediate processes. Okay, what do I mean by that? That here, you remember that we have a free particle propagator here. It comes in. This has energy h squared k squared over 2m. All this mess happens in the middle, okay? But then all these particles, I create one electron, this turns into a hole, creates an electron, it turns into a hole, okay? These photons are emitted and then absorbed, okay? So the end process, we have again a momentum k coming out. So this energy is h squared k squared over 2m. So if we just take into account the input and the output, the energy is conserved. But in the middle, this obeys no conservation law, okay? This is then called a, okay? Let me put it here. Energy is not conserved, okay? And this implies a virtual process. Okay, and if you know, if you've heard before this argument, or I'm sure you have from quantum mechanics, that you have the uncertainty relation. Okay, so virtual, let me describe here a little bit more what a virtual process is. So virtual process, here's the two C's. So a virtual process takes advantage of the fact that delta E times delta T has to be greater than h bar. So that means that we will have an uncertainty in energy in any process, in any quantum process, that's limited by this relationship here. Uncertainty relation. So if these processes become happen very quickly, okay, very quickly, this will be very small, this will be very large, and you can have large uncertainties in the energy. So lots of things can happen because of this uncertainty energy, these complex processes like this, okay, where you generate you have an electron, then this electron loses energy, and then you generate a particle-hole interaction, okay? And then this particle and hole disappear, and you recover your momentum. All these complicated processes can happen here because these are very short-lived processes, okay? And so this happen all the time in the vacuum. In the vacuum, you in principle have no particles, and then suddenly you have an electron and a positron come out and go back into the vacuum, okay? Okay, so you can, this happens also in particle physics. You have nothing, okay, and suddenly you have an electron hole or a positron, and an electron. This can be a ET, okay? So you have vacuum here, and you have vacuum on this side. And in the middle, you have these particle holes. And these particle holes, excitation can happen at any time. So this is just the analog in condensed matter is that you can have some electron jumping the gap, okay? So you create an electron here, and you create a hole associated with that, okay? A positive, and then this electron is created, and then it recombines here. So this will be the particle hole excitation. Okay, and this can happen just as in the vacuum for particles, okay, particle physics. Okay, it can happen also for a semiconductor, for example, or something that has a gap, okay, we can have a process like this going on. Okay, so this process in principle takes energies from from this uncertainty. Okay, so this can happen. Okay, can happen. Okay, even at t equals 0, so no thermal excitations, just because it's a very fast process. Okay, so this is what we call a virtual process. Although it may be sort of a ghostly-like, okay, a ghostly-like process, it is very important in determining the amplitudes of the processes we're going to see. Okay, so let me just illustrate. Okay, so let me just illustrate how momentum is conserved and
Excuse me, Ernesto.
energy is not conserved. Yes.
That hole will be the positron.
Yes, in the case of particle physics, it's going to be the positron. Yes.
And it exists.
Yeah, it exists. The positron exists in the Dirac sea, right? So remember that let me just put it here. So Dirac sea.
And in the case of the
have
semiconductors or transistors, is a positive charge, maybe.
Yeah, the hole is a positive charge. Okay, so it's exactly the same process. So you see that in the vacuum, you have in particle physics, you have you have the Dirac sea filled with electrons. This is the vacuum, and then you suddenly have you make an electron. It goes into the experimental range. Okay, so you have an electron here, and you leave a hole in the Fermi sea, and this is the definition of the positron. So it's exactly the same picture as that we have with semiconductors. You see, this is the picture of the antiparticle to the electron, the positron. Okay, let me just write it here. So positron is exactly the same picture as we have here. So you see how nature reuses the same physics in very different contexts. Here, this is the nature of the vacuum is the Dirac sea. The nature of the vacuum is the Fermi sea. Okay, so you can just translate all the tools that we're going to develop. We are going to develop some particular details associated with the nature of the potentials, for example. Then you can translate that directly to particle physics and these fluctuations of the vacuum. Okay. Okay, does that answer your question?
Yes.
Okay, good. Okay, so that's the nature of the virtual process. So let's see, and you'll notice here something that maybe you didn't digest when you studied basic mechanics, is that really momentum conservation and energy conservation are two separate conditions. Okay, so here we have a K plus Q, for example, any of the particular processes. Let's see which one. Let's choose. Well, let me do it on a separate. Okay, let me just illustrate here. Energy conservation with a question mark. Okay, so in the diagram, let's see what happens in the middle. So in the middle we have K minus Q, then flanked by these interactions. Okay, we have particle hole. So we have this labeling here. So let's see if at this moment, this is Q, this is Q here, and this is L. So let's suppose I'm trying to calculate more, energy conservation at this point in time, okay? So this is some time t, okay? So we have that, so if energy is conserved, then we should have this guy coming in, okay? And we should have that h squared, and then I'm not going to write too heavy notation, but this is the incoming energy. Okay? And this has to be equal, okay? Let me eliminate all these factors here, okay? So we should have k squared should be equal with the prefactor of this to, okay? This is a particle, this is a free particle propagator, so it has also energy h squared k squared over 2m, h squared L squared over 2m, okay? This is as much as an electron. This is a free particle propagator, so it has the same mass as this one, right? These are fundamental propagators, right? G naught, these are G naughts, okay, plus, okay? Should be equal plus, okay, the energy of this hole, so the energy of this hole is L minus Q squared, okay, plus the energy of this electron here, plus K minus Q squared, okay, if energy is conserved. Okay, it's clear that we have to multiply everything by h squared over 2m, right? So it will be on both sides. So when I can cancel both sides, this factor here, I know it has to be, okay, in front of this guy here, and in front of this guy, and in front of this guy, okay? I'm just canceling from both sides, okay? So this will be the condition. If you develop this, then you get k squared on the left, okay? And you get L squared, okay? And simplifying as much as possible, we get that this will be a k squared minus 2k dot q, okay? Plus q squared plus L squared, okay? Minus 2LQ, okay? Plus q squared. Okay, so you see that this is definitely not equal to the other one, okay? Here we see that we must have require some other condition, okay? We must require energy conservation so that this is restricted, because, you know, we can just simply cancel this guy here, and the sum of all these things has to be 0, okay? So energy is not conserved. And you see also that we're summing over Q and L, so Q and L are independent. Okay, so definitely energy is not conserved. Okay, so so this is the nature of things. Okay, this is how things work. So we're going to require momentum conservation. Okay, momentum conservation is always conserved, but energy is not conserved because this is going to be a virtual process. Apparently, the electron going in is the same as the electron going out, but this process is what we call the dressing, okay? Dressing of the electron. And this changes, okay, of electron, okay? And changes the amplitude. process. Okay? Good. Okay, so now that we have this kind of, we see that we have these kind of processes here, okay? As I told you, this is not going to be the simplest diagram, so we're going to start with the simplest diagram that can be built from the interaction, the two-body interaction we have, okay? And we're going to generate a perturbation expansion, making all the diagrams that we can imagine can happen, okay, using the free electron lines and the interaction lines, okay, conserving momentum. So those are the rules that we're going to have to obey, okay? So let's see how what type of diagrams we have, okay? And they're going to have immediate physical significance, okay? So the first one is going to be the tadpole. You know what a tadpole is?
Nope.
Anybody know what a tadpole is?
No.
No. Have you seen baby frogs? You know what a baby frog looks like?
Yes.
What does it look like? It has like a head like this, right? And it has a little tail like this, right? So that becomes a frog, okay? So frog. When it's a frog, it's an ugly thing. I won't even attempt to draw, but this is a tadpole. And this is why they put this name to the diagram. So the first diagram that we're going to see is something like this, the tadpole, baby frog. So, you know, physicists are very original in their naming things, right? So you can see that in the strong and weak interaction, there's lots of funny names for the quarks, for example. Okay, so let's draw the tadpole. So the tadpole is a free propagator coming in here with a momentum k, and then you have one single interaction. So this is a first order term, okay? First order in interaction, okay? And then the electron goes out, and that's it. So this happens at a particular time t, okay? And now we're left with what? We're left with a virtual excitation. This virtual excitation we're going to draw like this, okay? And the electron is going to come out with the same momentum that it came in, okay? And this we're going to label also with an intermediate momentum L, okay? Okay, so what's the interpretation? Before I put the arrow on this bubble here, I'll sort of interpret this. So an electron comes in, interacts, okay, with something. It may be a particle, it may be a hole, okay? So this is a single particle propagator. So this is going to be part of a, okay, of a single particle propagator that includes. So this is a single particle propagator. Okay, more advanced. I mean, there's some very complicated two-particle propagator techniques. Okay, this is beyond them, unless you want to specialize in this, but really it's not used very much. Okay, but with a single particle propagator, you have to have one particle coming in and one particle coming out. Okay, so if you put the arrow in this sense, okay, it's not correct physically, because you'll have two particles. Okay, so this one's going to the right. This is above the Fermi C. And if I put the arrow here, we'll have another particle momentum L above the Fermi C. So this cannot happen. Okay, another particle So this will be a two-particle process, a two-particle propagator, okay? So another particle above Fermi C. Not accompanied, okay? So this is not accompanied by a hole. Okay, so this particle cannot just appear above the Fermi C. It has to have a hole associated with it, like happened with the previous one, right? So this is a particle hole. So this is above the Fermi C, but you have a hole corresponding to it, right? Here, you cannot have this because of this, okay? So this is I'll put it here now, okay? So what can really happen is that with the interaction, you excite an electron out of a whole state, okay? Then you have your momentum, okay? Okay, then you have your wavy line, okay? And then you have your bubble, and the momentum comes out. But you can have this guy. Let me denote it like this. So now you can have an electron that excites another electron, creating a hole, and the hole is reabsorbed and disappears, okay? Hole, hole, electron, excited, okay? From below. Let me see. Okay, so we have an electron, we have the Fermi C filled, right? The interaction interacts with those electrons that are in the Fermi C, okay? So this produces a hole, and this hole is reabsorbed. So this is going to be a hole of momentum L. Notice that I draw the arrows very close to the vertex, so I can draw them backwards, so you understand that this is a hole. If you continue the arrow up to here, then you enter into a problem with the drawing, okay? Questions? I hear no noise. Okay? Okay, so this is one process. This is the tadpole process that can happen, and it can happen in two ways, okay? Two ways. Okay, remember that from this process here, so I started with my interaction with two handles. Okay, and here I chose to put this K here in the bottom, so I put K here and put K out. Okay, and then so this is coming in, this is coming out. Okay, and then I put L coming out. Okay, so these two are coming out, so K and L are coming out, right? Coming out and coming out, and then we have an L coming in. Okay. And then I joined them together. These I joined. And this is the tadpole. Okay? So how do we draw this? How do we write this? So we have the outgoing. We know that this is KL MN. It's not very convenient. I will confuse you. L R S T U. So no. So you know that this is the outgoing out, incoming. Sorry, in. You know that this is the incoming, and this is the outgoing. Okay. So this will be what process? So incoming are K and L. So incoming, K and L. Okay. And then the outgoings are going to be K and L here. So this is the KL process. Okay, so this is the matrix element we have to calculate. These are the labels we're going to use in the integral, in the first quantization integral. So it's completely specified by this, okay? Remember that we could have chosen also from the interaction, something like this, or also. Okay, you could have chosen the k on this side. K coming out as k. Okay, and L going in, L going out. Sorry. The other way around. Okay, L going in, L going out. Okay, and then we join these together. So this will be an inverted tadpole. This would be something like this, which is exactly the same. Okay, positive going, okay, okay, and then the hole moving in the other direction. Okay, so this would be the other diagram. But if you now write this, this would be we have to invert now. This will be the LK. Okay, so you see that this is a symmetry. This is the symmetry of the integral. If we swap at the same time these two labels and these two labels, we discussed it before, we arrive at this, and this is exactly equal. This is a symmetry of the integral, so both of those diagrams are the same. Okay. Okay, so these are the two types of tadpoles that can happen. Okay, this is the first diagram. Later, so that you can see the butter on the toast immediately, this is going to be the Hartree approximation. You've heard of the Hartree approximation before? Anyone?
No.
No, you haven't heard from quantum mechanics the Hartree approximation? Wow. So this is the approximation when you see multi-electron atoms, right, in quantum mechanics, you must have seen this with Henry maybe, and quantum 1 or 2. So you have the Hartree approximation. Okay. So this is so the Hartree approximation will just be described by this. You calculate this diagram and you summarize all the work that took this guy in order to calculate multi-electron atoms is just taken into account by this diagram. So you see how potent this theory is. Just from calculating an infinite series generated by this diagram, you calculate the Hartree approximation in atomic physics. Okay, so this is the first numerical work on many particle system was done with this approximation here. Okay, so this term will be the okay, so let me just tell you intuitively, because we're going to show it in analytically afterwards, what the Hartree approximation is. The Hartree approximation is something very intuitive from the point of view of electromagnetics. Okay, so in principle, okay, we can only solve, and the dogs have begun. Okay, so we only know Jesus Christ. We only know how to solve the hydrogen atom. Okay, we don't even know how to solve the helium atom, so that you know. The helium atom is just adding an extra electron, and we still can't solve it exactly. So you can imagine how difficult these problems become very quickly. Okay, so we know the hydrogen atom, so we know we have a single nucleus. Okay. Okay, and your electron orbiting around the. Okay. Okay, so what happens if you add lots of electrons now? Okay, and you start adding positive charge to the nucleus. Okay, and you have all these electrons. Okay. Okay, so how do I treat something as complicated as this? So, you know, if you can't calculate exactly with 2 electrons, you know, you have no hope to calculate the uranium atom, for example. Okay, uranium. So what do? What people did was numerical work, and they assumed that, okay, this is a central potential problem. So you have an electron in each of these orbits. This is just a caricature. You know, you have, I know you have densities and all this. Okay, so you imagine all these electrons. So you pick out one of these electrons and assume the rest of the electrons, okay, make a spherical potential. Okay, so you separate one electron. This is in your imagination, and imagine the rest forms a spherical potential. Okay, and you see the interaction between this electron, that spherical potential. So that's a very easy problem to solve. So that essentially what the Hartree approximation is a mean field approach. Okay, and we'll see, hopefully we'll get to magnetism, so we can see what the mean field approach is in other contexts. Okay, so that's essentially the idea, and that's the idea that's captured precisely by calculating this diagram. Okay, if you calculate this diagram, then I can calculate this approximation. Okay, so let me put here just the tadpole. Okay, remember that that we had to take into account that we're dealing with fermions. Okay, so if we're dealing with fermions, we need to take into account a second type of interaction, a second type of diagram. Okay, that takes into account the fermionic character of the electron. What is this second diagram? The oyster diagram. You know what an oyster is? Anyone?
No, no sé.
No one knows that. Don't you like to these shells that they sell at the beach with a little lemon, and you take it in?
Las ostras.
Ah,
That's an oyster is an ostra. Okay. Okay, and you'll see now when I draw the diagram, okay, that it's just like an oyster. So you would draw an oyster like this. Right? This will be the drawing of an oyster. So this is exactly how you draw your diagram. So let's go back to blue here. So now we have something like this. Let me draw it in the other way. So we have the interaction like this. Okay. So now I'm going to make a combination which I didn't do before. So I put in a K here, okay? And now I'm going to have an L going out here, okay? Now I'm going to have an L going in here and a K going out the other end. You see that this is very different from the one I had before, because here I always had the K coming out of the same coordinates. So remember, this is R and R prime, okay? So K was coming out from the same end of the interaction, okay? Here again, the K is coming out from the same end of the interaction. Now we swap them. You see, K is coming in here and it comes out here. So we join these lines together here and we have another diagram, which is a first order diagram. So let me draw it how you would draw it now in the calculation. So you have now a K vector going in, okay, the interaction, okay. Now the K vector going out here. And we have a whole line coming out here. And this I label with L. Okay? So this is you call it oyster, but it's really a half oyster diagram. Okay? So this is why they call it the oyster diagram. Again, you know, physicists like to joke around with the diagrammatic. So, you know, they're called different. They're drawn differently and associated differently to. There are much more boring ways to write this, but it's much more fun to give them names and, you know. Okay, so you can have this.
In this case, it's like the particle is going in to the right and then go back.
So this again, instead of
and then interact with a photon that previously emit.
Right. So this is again, this is going to have some momentum here. Okay. So I have an electron. The interaction generates a hole that is recaptured. And now the momentum L is exchanged with the K momentum of the electron. So you see? So this is called the exchange interaction. And I think you must have heard this in previous quantum mechanics courses. So this would be the direct interaction. The tadpole is the direct interaction. So you go, you scatter, okay, and a hole out of an electron out of its state and generate a hole, okay, and then this hole is reabsorbed and then you continue, right? So first the momentum flows in this direction, then it flows in the other direction, okay? So netly we have 0 K. This will be, we would have Q equals to 0 here, okay? Because no net flow of momentum in this direction, because it first flows in this direction, then it flows in the other direction. Here, we would have, okay, K, then we have L, so we have K minus L here, and then K minus L joins with the L and brings back the K on this side. So as we're exchanging sides, okay, so again, this is R and R prime, okay? So we exchange sides. We exchange one particle with the other, so we get the exchange interaction, okay? So if you add the exchange, so direct, okay, or Hartree plus exchange, you get the Hartree-Fock interaction. So just with these two diagrams, we're already doing calculations at the level of the Hartree-Fock interaction. Amazing, okay? And we'll see how then you combine these two diagrams in order to generate an infinite series that gives me the Hartree-Fock interaction, okay? So remember that we can also combine this in a different way, so we can, so this will be another way to generate the the oyster diagram. Okay, so now K is coming on this side, okay? Then this will be L, and this combines like this, L, and goes out like this. Okay, so this will be drawn in the same way I drew it above. So now we're coming in with the K, okay? We have here the L coming out here, okay? And the K coming on this side. Okay, again, when you draw the interaction associated with this and try to work it out as we worked it out before. So this will be either the V K L L K or the V L K K L. Okay, these are two. This will be the same. Okay, because again we're swapping the two labels at the same time, so this is a symmetry of the integral. Okay, okay, same value. Okay, but notice that in contrast, okay, let me just put it here. So it's not the same integral, not the same as the VKL KL, which is the Hartree, and this will be the other contributor to the exchange. So those two integrals are going to be different, okay? And we're going to calculate both integrals exactly, okay? Any questions up to here? Okay, so let's do one more calculation before ending the class. I'll just translate this with the Feynman rules, okay? So here we have Feynman rules. Okay, now, you know, so that we have fun here, we'll put it the other way around. And continue in blue, okay? So let's translate this diagram here, the tadpole diagram, following our Feynman rules. Okay, so let's label it so we know what momentum associated with each. We have K and K. We have that happens at T1, it comes out at T2, and we have T in the middle. Okay, so what is this diagram here? I'm going to leave a space for something, a new element that we're going to have here associated with the values of having loops like this. Okay, I'll put this at the end. This is a new Feynman rule that we're going to have to follow. Okay, so we have a summation over an integral over t. We have an intermediate time, so we have an integral over t. Okay, this is going to from minus infinity to infinity, and you know that these limits are governed by the forms of the Green's functions. Okay, and we are also going to sum over all the L values, and all the L values are below the Fermi C. So we have this is below the Fermi momentum. Okay, because these are all holes. Okay, so these are two. So we're following, you know, following our noses with the Feynman, and then we write the propagator. So we have one propagator here, a momentum K. So we write I G naught plus. Okay, and we have K going between T and T1. Okay, then we have the interaction. Okay, this wavy line here with the corresponding labels will be minus I over 2 minus I over 2 V KL KL. Okay, and then we have, let me close here, okay, and then we have the propagator associated to the bubble, which will be a Hall propagator. So this is I G naught minus, okay? So this is the bubble, and it goes from T to T, okay? So it has some momentum L, okay? And it goes from T to T, that is 0, is the second argument. And finally, we write this propagator here. Okay, so this is multiplied. This is also inside the integral, so I G naught plus, then we have K, okay, and T2 minus T. Okay, do you agree with this interpretation of the Feynman diagram? So you should have 1, 2, 3 propagators, 1, 2, 3 propagators, 2 of them a retarded propagator, so these are these 2 pluses. Then we have an advanced propagator, which is this guy, and we have the interaction. So we've drawn everything. We have to integrate over intermediate times and integrate over all the possible momenta of the hole here, okay? One additional rule is that each time I find this loop here, I have to put a -1. And this is fermion loop, and this is the last rule we're going to have for the Feynman diagram, fermion loop. Okay? Of course, you do this with a table, so we're going to, at the end of this section, we're going to do a table with the new Feynman rules, and then each time we see a diagram, we just translate it into the mathematical expression and calculate, okay? The thing is that we're going to do all the calculation in terms of the diagrams first, so we reduce to the minimum the number of integrals we have to do, hopefully 1 or 2 at maximum. And when we do those integrals, we will have a sum the whole series. We don't have to do a calculation for each diagram in the series. And you know how we will do this, okay? Just as an advance, for example, the Hartree approximation, will be this expansion. So we go to Fourier space, remember, this is a mesh in KT space, so we go to in K omega space, and we'll do that first thing next class. Then again, we get the free propagator. Then we get the first tadpole. Okay. And then we assume that the tadpole is the only important diagram. So, but we know we have to sum infinite diagrams, but we don't care about the oyster or any more complicated diagrams. We assume that this is the approximation we're doing. Okay. So we have now 2. Okay, plus 3.
Profe,
Yes.
is possible to have a loop counterclockwise? Maybe it can change the sign of the G of the propagator, and maybe it can change the -1 in front of the summation.
Right. So, so we'll find out that this equal time loop will give me a -1. Okay. We'll show that next class, and this will cancel the -1 here. Okay. And the only one we can, we cannot have a loop going in the positive direction because of the problem I mentioned with this diagram. We cannot have a loop going in the other direction, but we can have particle hole loops like this. And this is also a fermion loop, okay? So you can have a particle as long as it's compensated by a hole. But you cannot have in the single particle expansion, you cannot just have a counterclockwise loop, okay? That is forbidden, because that would imply you have 2 particles at the same time instead of having just one particle propagator. Remember, you have the 1 particle propagator, but you have a 2 particle interaction, okay? That in the context of these diagrams, these also always has to happen between particles and holes, okay? So you generate this expansion, and this is the Hartree expansion, and we can sum this exactly. This exactly. So you notice how we make contact with the Hartree approximation. We're going to write this in first quantization and show you that this is exactly what you would expect from the mean field approach for example, a multi-electron atom or a multi-electron electron gas. Okay. Okay, so let's stop here unless you have some more questions, and we'll continue tomorrow. Any other questions?
I'm fine.
No? Anybody else? Ajá.
Cuando se crea un positrón y un electrón, ¿sería posible? Se supone que en el vacío se crean y luego se encuentran de nuevo y se eliminan.
Correcto. Claro, porque...
¿Y sería posible separarlos con campos magnéticos? Que se separen y dejar aislado el positrón y en otro lado el electrón.
Claro, o sea, let me explain. So that's a good question to distinguish virtual from real processes. So remember that virtual processes, so you can have an electron positron process, right? So you have an electron and a positron going like this, and this, you had nothing, okay, nothing here and nothing here, okay? This can only happen for a very small delta t, very small delta t, because that implies that we have a very large energy uncertainty, and if this is sufficiently small, this can be of the order of half a mega electron volt. So you can pay the price to go from the Dirac C, okay, to the positive energies, and then go back, okay, in a very short time. So very short time you can have, but if you, like you say, you apply a very strong electric field, okay, and that field, okay, if you apply a very strong electric field, so let's put it like this, electric field, okay, and that field is able to promote an electron from the Dirac C to the positive energies, then you pay for this. So you don't need the uncertainty principle. So this would be a real process, not a virtual process. Okay, this will be a real process. Okay, this will be a virtual process. Okay, so you really extract an electron from the Dirac C, and now you will have an electron going in one direction, okay, and the positron going in some other direction, and you create real particles, okay. So this is the difference. Either you pay it with uncertainty, which is the virtual process, or you pay by putting in the energy you need. For example, if you hit the vacuum, you have a gamma ray or a cosmic ray just propagating, there's a finite probability that that gamma ray gets absorbed by an electron in the Dirac C in the vacuum and just generates a particle-hole pair, okay? And these will be real, and this electron just goes to the Earth and the positron goes somewhere else, okay? Conserving the momentum, because you could have a gamma ray, for example, here, which has sufficient energy, and this gamma ray generates an electron, and the process is such that the momentum, okay, you have to conserve the momentum, so the momentum of the gamma ray has to be the sum of the momenta of the electron and positron, okay? So these had to add up. Okay, and you generate real particles in the process. Otherwise, the effects that we're currently seeing are associated with these virtual processes. Okay, these are real processes. Okay, that's the difference between the two. Is it clear?
Sí, gracias.
Okay, any other questions?
The time of production of positron and electron is related with the time that we can extract of the Heisenberg principle.
Right, precisely that. So, so if you calculate delta E, okay, it has to be larger than h over delta t. So if this is going to be 0.5 mega electron volts, you can calculate from that time, and I leave that as homework. What is delta t? So you can tell me how short the lifetime would be, the lifetime of this particle. Okay? Calculate this for tomorrow. Tell me how many femtoseconds, or I don't remember the lower, petaseconds we need, we can have this process going on. Okay?
Okay.
For tomorrow.
For tomorrow.
Calculate this. This is a very short calculation. You just have to know the Planck's constant. You know this in mega electron volts. Calculate delta T. Okay? Okay, people. So see you tomorrow then.
Bye, professor.
Bye-bye.
Yeah.
Mañana.
Chao, hasta mañana.
Profe, ¿cómo está? No había
Ajá.
podido asistir a las clases anteriores. ¿Cómo está?
Ajá, ¿qué tal?
Sí,
Ismael.
le envié un mensaje. Sí, Ismael,
Sí.
exacto.
Sí.
Le envié un mensaje la anterior vez. Ahorita estoy con datos de mi celular. Mi conexión a internet está pésima.
Ok.
Ya me rendí con esa cosa y ya me tocó ponerle los datos al celular.
Ok.
Ya. Profe, si no estoy mal, creo que enviaron un deber, aparte de, por supuesto, calcular ahorita el tiempo en segundos que
Sí.
sería.
Sí, tenemos un deber ahí. Ajá.
Quizás podría pedir una prórroga para primero ver ahorita, primero tengo que conseguir donde mis tíos, aunque sea que me presten un momento el internet para descargar las clases que están en el
Ok.
entorno, verles cómo están las clases y de ahí para hacer ese deber. Quizás podría pedir eso.
Déjame ver qué fecha puse de límite. Creo que
Claro.
era para mañana, creo. Creo que era para mañana. Pero entonces, preguntarle a los demás estudiantes y los extendemos todos.
De acuerdo.
Quizás podemos hacerlo para el próximo lunes en vez de para y les pongo la nueva tarea en el...
Muchas gracias, profe.
Ok.
Muchas gracias.
De acuerdo.
Perdón por no haber podido conectarme en estos días.
No es culpa tuya, está fuera de tu control en esta hecatombe mundial.
Sí. Hoy estuvo bastante interesante para que también, junto con la del abuelo, los perros, una joya. Una joya.
Sí, señor.
Una joya.
Chévere.
Bueno.
Bueno.
Profe,
Chévere.
muchas gracias.
Eso.
Hasta luego.
Hasta luego.
Buenas tardes.